We're surrounded by these incredible feats of engineering, right? Bridges, cars, planes, you name it. But what we don't always see is that every single one of them is in a constant, hidden battle with the forces of nature. So in this explainer, we're going to pull back that curtain and get to the bottom of a fundamental truth: why, eventually, materials fail.
I mean, it's something we've all seen. That old car in the driveway starts to rust. A metal tool just snaps in your hand. Or that plastic chair you left out in the sun gets all brittle and cracks. It feels like it's just meant to happen, but it's not random at all. There's a real science to why things break down, and honestly, understanding that is the absolute key to building things that actually last. Okay, so this fight for survival for any material, it really happens on two main fronts. On one side, you have these slow, relentless chemical attacks coming from the environment. And on the other, you've got these sudden, powerful smack of physical force. Let's break down the key players in this war. So the first player on the field is corrosion. You can basically think of it as nature's own recycling program. See, when we refine metal from ore, we're pumping energy into it to make it useful. Well, corrosion is just that metal trying to release all that stored up energy and get back to its original, more stable, natural state. The most famous example, of course, is iron reacting with oxygen and water to create iron oxide, which we all know as good old rust. Now, on the physical side of the battle, we have deformation. This is pretty straightforward. Anytime you apply a force to a material, you pull it, you push it, you twist it, you're trying to change its shape. The material's internal structure is fighting back. But, every material has its breaking point. And when you push past those limits, you get a fracture. This is it, the end of the line. It's that moment the material just can't hold itself together anymore, and it separates into pieces. It's the catastrophic end to the fight against stress. All right, let's take a closer look at that first attacker, corrosion. Now, this isn't some loud, explosive assault. Now, it's more like a quiet, persistent siege, working day and night to undermine materials from the surface all the way in. And here's the thing, not all corrosion is created equal. Some types are super obvious, like a sheet of metal just evenly covered in rust. But others, they're way more sneaky, hiding out in tiny crevices or working their way deep inside the metal structure, weakening it without any visible signs until it's just way too late. And these attack methods are fascinatingly specific. You've got uniform corrosion, which is that even spread of rust we're all used to seeing. But then there's pitting, which is way more aggressive. It literally drills deep, tiny holes into a material. Crevice corrosion loves to attack tight spots where there's no oxygen, like right under the head of a bolt. And then there's galvanic corrosion. This is what happens when two different metals touch. The more active one basically sacrifices itself to protect the other. But maybe the most dangerous type of all is intergranular corrosion. Okay, imagine a brick wall. This kind of corrosion doesn't attack the strong bricks themselves, no, it attacks the mortar between them. It follows the boundaries between the metal's grains, causing a total loss of strength, even when the material looks perfectly fine from the outside. And this leads to a pretty terrifying combination: stress corrosion cracking, or SCC. It's a real double whammy. You take a material that's normally tough and flexible, a ductile metal, and you put it in a corrosive environment, and you put it under physical stress. The result? Sudden, totally unexpected cracks that can lead to catastrophic failure. So that's the chemical attack. Now let's flip over to the other side of the battlefield, the direct assault of physical stress. This is what happens when a force is just plain too much for the material to handle. When a material gets stressed, one of two things is going to happen. First, you might get elastic deformation. Think about stretching a rubber band. You change its shape, sure, but when you let go, it snaps right back to normal. That's reversible. But if you push it too far, you get plastic deformation. Now think about bending a paper clip. It stays bent, right? That change is permanent, and the material is now weaker for it. So what happens when the material finally gives up and breaks? Well, the big question is, does it give you a warning? A ductile fracture is actually safer because the material stretches and bends and deforms a lot before it fails. But a brittle fracture, that's way more dangerous. It happens suddenly with little to no warning at all, kind of like glass shattering. In engineering, avoiding brittle failure is absolutely critical. The way a ductile material fails is actually a pretty cool process to watch, in a way. First, when you pull on it, it starts to neck down, focusing all that stress into one spot. Then, inside that neck, these tiny little voids, like microscopic bubbles, start to form.
These little voids then grow and link up, creating a crack that spreads out until, snap, the final fracture. And it leaves behind this really distinctive cup and cone shape on the broken ends. But hey, failure doesn't always come from one big, dramatic event. What if a force isn't strong enough to break something, but it just keeps getting applied over and over and over again? Well, that's when fatigue sets in. The material literally gets tired. Each tiny little push or pull, repeated millions of times, creates damage that just adds up until it leads to a sudden, complete failure.
Fatigue failure basically happens in 3 acts. Act 1, crack initiation. A tiny, microscopic crack forms, usually at some little surface imperfection. Act 2, slow growth. With every single stress cycle, every vibration, every load, that tiny crack gets just a little bit bigger. This can go on for years. Then, Act 3, rapid fracture. The crack finally hits a critical size where the rest of the material can't handle the load anymore, and the whole thing fails suddenly and completely.
And finally, we've got the marathon runner of failure, creep. This is the slow, permanent stretching of a material that's under a constant load for a really long time, especially when it's hot. Imagine a heavy bookshelf. Over decades, those wooden shelves might slowly start to sag under the constant weight of the books. That's creep in action. It's not fast, but it gets there. So we understand the enemy, right? We know all the different ways materials can be attacked, chemically and physically. And the good news is, by understanding the attack, we can come up with a defense plan. This is where engineering really starts to fight back.
The first rule of defense is simple. Know your battlefield. Engineers have to analyze the exact conditions a material is going to face. Is it going to be wet, hot? Is it going to be under constant vibration? Only when they know that can they choose the right material and the right protection strategy for the job.
So to stop corrosion, engineers have this 4-part arsenal they can deploy. First, they can use a physical barrier, like paint or a special coating. Second, they can choose materials that are just naturally resistant, like stainless steel. Third, they can add chemical compounds called inhibitors that slow the whole reaction down. And finally, they can use this really clever trick called electrochemical control, where a sacrificial piece of metal is designed to corrode instead of the important structure. Pretty smart, huh? All of these prevention strategies, from picking the perfect alloy to designing joints that avoid brittle fracture, they're really the armor that our modern world wears. It's this deep, deep understanding of failure that lets us build things that can actually win that long, slow battle against the forces of nature. When it's all said and done, it comes down to this one simple but really profound idea. Every broken part, every rusted beam, every cracked component, it's a lesson. By studying the anatomy of failure, we learn how to engineer success. Understanding why things fall apart is the single most powerful tool we have for building a world that actually holds together. And that, of course, brings us to the future. We're constantly inventing these new materials, composites, advanced polymers, incredible new alloys, and with every new creation comes a whole new set of challenges and, yeah, probably some new and undiscovered ways they might fail. The battle for durability, it's a fight that never truly ends.